Welcome all of you. I am Vishwas Kare from SSR College Silvassa. In this tutorial, we'll talk about examples of vector space. Example: let V is equal to f a comma b, which is equal to set of collection of all functions from a comma b, close interval a comma b to R. That is, V is a set of all real valued functions defined on close interval a comma b. For f comma g belongs to V and alpha belongs to R, we define f plus g over x is fx plus gx for all x belongs to close interval ab, and alpha f over x is equal to alpha times or alpha dot fx for all x belongs to ab. Show that V is a vector space. To show it is a vector space, we'll show that all 10 properties of vector space are satisfied. First, if fg belongs to V, then f plus g over x is equal to fx plus gx by definition. Now fx is a real number, gx is a real number, so f plus gx belongs to R, that is f plus g is a real valued function, hence f plus g belongs to V. Second, for all f comma g comma h belongs to V, we have f plus g plus h over x is f plus gx plus hx by definition, which is same as fx plus gx plus hx. Now fx, gx and hx are real numbers, and real numbers follows associative law. So this can be written as fx plus gx plus hx, which is same as f plus g plus h x, again by definition. Hence, we have the function f plus g plus h is equal to f plus g plus h. Third, there exists 0 belongs to V such that f plus 0x is equal to 0x plus fx, which is equal to fx for all f belongs to V. Hence, f plus 0 is equal to f. Similarly, we can show 0 plus f is equal to f. Here, function 0 is 0 element or 0 vector of V. Fourth, for each f belongs to V, there exists minus f belongs to V such that f plus minus f over x, which is same as fx minus fx, is equal to 0. Similarly, minus f plus f over x is minus fx plus fx is equal to 0. Hence, f plus minus f is equal to 0 vector, which is same as minus f plus f. That is, inverse element of each element exists. Fifth, for all fg belongs to V, we have f plus g over x is same as fx plus gx. Again, these are real numbers, can be written as gx plus fx, which is same as g plus f over x by definition. Hence, we have because f plus g over x is same as g plus f over x. Hence, f plus g is equal to g plus f for all fg belongs to V. Sixth, for f belongs to V and alpha belongs to R, we have alpha f over x is alpha times fx, again by definition for all x belongs to R. That is, scalar product satisfied. Seventh, for all fg belongs to V and alpha belongs to R, we have alpha dot f plus g over x, which is same as by definition alpha dot fx plus gx. Now fx and gx are real number and alpha is a real number, so it is can be written as alpha dot fx plus alpha dot gx, which is same as alpha dot f plus alpha dot gx. Now again, alpha dot f plus g over x is same as alpha dot f plus alpha dot g over x. Hence, we conclude that alpha dot f plus g is same as alpha dot f plus alpha dot g. Eighth, for all f belongs to V and alpha beta belongs to R, we have alpha plus beta dot f over x is same as alpha plus beta dot fx, which is same as alpha dot fx plus beta dot fx, which can be written as alpha dot f plus beta dot f over x. Again, the function alpha plus beta dot f over x is same as alpha dot f plus beta dot f over x. Therefore, we conclude that alpha plus beta dot f is same as alpha dot f plus beta dot f. Ninth, for all f belongs to V and alpha beta belongs to R, we have alpha beta dot f over x is same as alpha beta dot fx. By definition, it can be written as, again, alpha is a real number, beta is a real number, fx is a real number, which can, so it can be written as alpha in bracket beta dot fx, which is same as alpha dot beta dot f over x. Hence we have alpha dot beta dot f is same as alpha beta dot f. And there exists one belongs to R, for which we have 1 dot f over x is 1 dot fx, which is fx, because fx is a real number, 1 is a real number, their multiplication is a real number. Hence 1 dot f is equal to f, for all f belongs to V. And as all properties of vector space are satisfied, hence V is a vector space. Example. Let V is equal to xy belongs to R2, where x and y are greater than 0. For all u is equal to x1, y1 and v is equal to x2, y2 belongs to V and alpha belongs to R. Define plus and dot operation as u plus v is x1 plus x2, comma y1 plus y2, and alpha dot u is equal to alpha x1, comma alpha y1. Show that V is not a vector space. Solution. Again, we'll show one of the 10 properties is not satisfied. Solution. With given operation, the 0, that is 0, 0 is a 0 vector, but 0, which is 0, 0 does not belongs to V, because V contains all tuples on which x and y are greater than 0. Hence V is not a vector space.